Okay, last time, of course, we talked about matrix inverses, and we specifically took the point of view that matrix inverses are about functions, like so much in this class, that we take functions as the primary object and that we take the matrices as kind of the computational aspect of functions. That doesn't mean that matrices are foolish or we look down on them. It just means that something has to come first and we take functions to come first. We've seen a couple of examples of that happening and we'll see more today. But so anyway, the check-in, of course, is about inversions, and specifically it talks about the inverse of a function. So let's get to it. Okay, so let's see what I got for a function here. F takes the plane to the plane. Okay, and the action is what? xy goes to, it's x plus 3y, and 2x plus 4y. All right, and then we're looking for the inverse, g. So g has to start at f's codomain, so f's range, r squared, and has to end up where f started. Again, those are the plane in all four cases, but anyway, that's the idea. And rather than say xy here, which of course would be perfectly sensible, but I'm going to say, in the hopes that it'll cause less confusion, x hat and y hat. X hat and y hat. So I don't know what they are. If I knew what they were, I'd be done. So let's just call it a x hat plus b y hat and c x hat plus d y hat. So some general map from the plane to the plane. It takes the inputs x hat and y hat and it does things to them. And let's suppose then that I'm looking to find that g circle f of the input is the input back again. So I want g to be the inverse of f. Okay, so let's see what to do. So I'm gonna take x, y, and under the map f, it's supposed to go to x plus 3y, 2x plus 4y, and then when you subsequently apply g, as you do here, it's going to go to, let's see, it's a times x plus 3y plus b times 2x plus 4y, and then c times x plus 3y plus d times 2x plus 4y. And let me gather together the x's and the y's there. What am I looking at here? I'm looking at a plus 2b x and 3a plus 4b y. And on the bottom I've got c plus 2d x and 3c plus 4d, 3c plus 4d y. And of course the whole thing, when all is said and done, is supposed to be the identity, so we're supposed to end up with xy. Now I don't know what a, b, c, and d are. That's the goal of the question, is to figure out what a, b, c, and d are. But I know that a plus 2b is 1x. 3a plus 4b is 0y, and like that. So as so often in this class, we're looking at a linear system. We've got a plus 2b is 1, and 3a plus 4b is 0, and then c plus 2d is 0, and 3c plus 4d is 1. All right, so Gauss's method. I won't bore you with the agony of watching me do arithmetic, so instead I'll just say that after a while I was able to work out that minus 3 row 1 plus row 2, followed by minus 3 row 3 plus row 4, leaves you with this linear system. A plus 2b equals 1, minus 2b equals minus 3, c plus 2d is 0, and negative 2d is 1. Okay, so the Gauss's method stuff, we're all great at Gauss's method at this point, so we're not going to go into that at great length. And so when all you can see from the bottom line, when you get down to the end, you're looking at D is minus a half. If D is minus a half, then C is 1. The next line up tells you that B is 3/2. And the next line up tells you, let's see, if B is 3/2, then I'm looking at A plus 3 equals 1, so A is minus 2. Okay, so I was able to figure out here what happened with the, oops, excuse me. I was able to figure out what happened, what are the A, B, the C, and D that would work. You've seen me do calculations before. It's always a good idea to check. So I'm going to try it with a specific example, just to try to make some sense of. So I'll take 5/6. So let's see, what does F do to 5/6? So x plus 3y is 5 plus 3 times 6, so that's 23. And 2x plus 4y is 2 times 5 plus 4 times 6, so that's 24, and 10 is 34. And then what does g do? Let's see, I've got here minus 2 times 23, and then b times 34, so that's plus 3/2 times 34, and then 23, that's 23, that's c is 1, so 23 minus 17. And what the heck is this? This is minus 46 plus 51. 23 minus 17, so I got what I was supposed to get, 5/6. So the effect of G following F is the identity. Acting from the left, G is an inverse of F. Okay. So again, last time we talked about the inverses of functions and left inverses and right inverses and double-sided inverses. Let's get back to it. So we ended up last time with the definition of that G is, oops, there we go, G is a left inverse of H if G, capital G acting on the left on H produces the identity matrix. The right inverse if capital G acting from the right on H produces the identity matrix. And the case that we'll think about most often, capital H, so a matrix is with a two-sided inverse is called an invertible matrix. And the two-sided inverse is denoted H with a superscript -1. And all this exactly fits with what happens for functions. And of course, we did a couple of examples last time, and I pointed out one reason why a person might want to think about taking the inverse of a matrix is that it makes solving these systems very fast. Okay, so this is material that we didn't see last time. I took the regular function composition arrow diagram that we saw when we were doing matrix multiplication, and I specialized it to the case of the identity map, when the function composition is the identity map. And that's what we're looking at. We're looking at if you do H first and then follow it with H inverse, you get the identity function. All right, so one thing to notice about this version of the arrow diagram is that in the previous version, it said V to W to X. Here it doesn't say V to W to X. Here it instead says V to V. And that's simply because the identity function takes capital V in and gives capital V out. That is, the identity function mapped capital V to capital V. Still, another thing to see here is that I have, of course, the matrix capital H and the matrix capital H inverse. And on the bottom here, I have the matrix capital I. That's the identity matrix, the one that's square. All zeros except for ones down the main diagonal. Because capital I is the identity matrix, that says with respect to the basis B, and that also says with respect to the basis B. Okay, so this is the arrow diagram for composition specialized to the special case that we want to consider. So as usual, when we introduce an idea here, for example, to relate the representation of the map, capital H, excuse me, lowercase h, with the representation of the map, lowercase h inverse, whenever we introduce an idea, we try to surround it with some ideas to help a person sort of build up the right structure in their mind, the right scheme in their mind to hang later ideas off of. All right, so here's a picture version of the sort of algebraic statement that we gave earlier. Okay, have a couple of results that we're not going to prove. The proofs are usually easy. I'm going to mention one of them. The proofs are usually easy, but I happen to want to get to the computation of matrix inverses. That's the goal for today. So I'm going to go a little light on the proofs, but I'll just mention. If a matrix has both a left inverse and a right inverse, then the two are equal. So it cannot be the case that a matrix has one inverse on the left and one inverse on the right, and they're different. That can't happen. And I'm just going to mention here what the idea of this is. The idea is you imagine that capital H has both a left inverse A and a right inverse B, and then you look at what happens when you take A times H times B. On the one hand, it's A times H times B, which is B, because that's the identity. On the other hand, it's A times H times B, which, you guessed it, is A, because that's the identity. So B and A are the same. Okay. So so a lot of these results here are the same idea, that it's just a question of thinking through what the maps are doing. So here we're looking at the second result says a matrix is invertible if and only if it's non-singular. And again, that's the same idea as we saw before. Non-singular matrix is associated with a non-singular map. Map is non-singular if and only if it's an isomorphism. You go from V to W and you can come back. Well, that's the same thing here. A matrix is invertible, means that you can multiply it and then you can undo that to come back. Now both of these results have quick proof. You start with a matrix, because both of the results say start with a matrix. You start with a matrix, you fix spaces capital V and capital W, and then you fix bases, you might call them capital B and capital D. And then you just look at what happens with the arrows. Capital H represents a map lowercase h, and the statements are true about the map. If a map has both a left and right inverse, then the two are equal. So the statements are true about the map, and therefore they must be true about the matrix. So the idea again is we're taking maps as kind of the original object, the sort of object, and we're worried here about seeing how that's reflected in the computational entities, the computational things derived from the maps, the matrices, and it just falls right out. Two more results. Again, the first lemma says product of invertible matrices is invertible. If capital G and capital H are invertible, then capital GH is defined, then capital GH is invertible also. And capital G, capital H inverse it's not what you might think it. You might think it's capital G inverse, capital H inverse. That's not right. Instead, the inverse of capital G, capital H is capital H inverse times capital G inverse. But this is easy to see. You just say to yourself, what does it take to get rid of GH? Well, first you want to stick in a G inverse to get rid of the G. Let me go to the scratch work. There we go. So what does it take to get rid of GH? And of course, what you want to do is get rid of the G first. Those will cancel to give an identity. And then after that, you can get rid of the H. So you get rid of the G first, and then the H and H inverse, and you do indeed get the identity. Okay, so that's just a question of sort of writing things down in the right order, and exactly the same argument as above. Exactly the same argument works for the functions. Okay, and then finally I'm at the result that I want to get at. The result that tells you how to compute the inverse of a matrix. So a matrix H is invertible if and only if it can be written as the product of elementary reduction matrices, and then here's the part that we're going to focus on today. We can compute the inverse by applying to the identity matrix the same row steps in the same order that you use to Gauss-Jordan reduce H. So this says how to compute the inverse, so we're keen because we want to get the answers. In the back of the book, that's always interested in finding the answers. Again, I'm not going to go through the proof, but again, the proof is got a simple idea to it once you think about stuff we've done before. So we want to find G so that GH equals the identity. So what is it? What is it that multiplies H to give the identity? Well, we saw when we were doing the mechanics of matrix multiplication that there are matrices that do the Gauss's method steps. I'm here at H, I want to get to the identity, so I want to do the Gauss's method steps that do Gauss-Jordan reduction. So we saw a result last time that says there's a sequence of matrices. I think I called that last one capital R sub little r, where if you multiply them together, then you're doing the Gauss-Jordan steps that take H to the identity. So this is exactly what I want. This is capital G. Multiply those matrices together. Stated in the form of the lemma, I'll write capital G as, write them out here, and I'll multiply them all times the identity. That is to say, I'll start off with the identity and then do R1, and then after that I'll take the result and do R2 to it, and after that I'll take the result and do R3 to it, and etc. And that's all it is. I'm just simply recognizing that Gauss-Jordan reduction is what I want to do, and that the steps of Gauss-Jordan reduction, if performed on the identity matrix, will result in the matrix capital G that I want. So let's see an example. Okay, so here's a matrix that is non-singular, and so therefore it's invertible, and I'm gonna of course find the inverse. So it's non-singular, square, and if you do Gauss's method on it, you'll get echelon form with no zero rows. So, all right, so let's do the steps I just described. So the steps I just described is you start with the identity. See the identity over here? This is the matrix capital A, and this is the identity. You start with the identity, and you perform on the identity the Gauss-Jordan reduction steps. So that's what I'm doing. I wrote the identity next to the original matrix. I'm performing the Gauss steps here. I didn't all fit on one slide, so I got to do more on the next slide. I'm performing the Gauss steps here. For example, minus 2 row 1 plus row 2 is how I use this one to get rid of that 2. And if I follow it all the way across the row, minus 2 row 1 plus row 2 puts this minus 2 right there. Likewise, minus row 1 plus row 3 gets rid of that 1 and also puts a minus 1 here. And you continue along in that way in the usual Gauss's method way. And again, the Jordan half of Gauss-Jordan is on the second slide. I just couldn't fit it all in one slide. Here I have echelon form. Next step in Gauss-Jordan's reduction. Do you remember the next step? The next step is to turn all of the diagonal elements into ones. So I have to multiply row 2 by minus 1/6, and I have to multiply row 3 by minus 2. Make some messes over here on the other side. And then here you go. You have to take the entries, remember, in the opposite order, moving from right to left now instead of left to right. You take the entries and you eliminate up. And you eliminate up. When you do, follow through the arithmetic, you get this. That is the answer. It has a disadvantage of being a bit of a mess. It has the advantage of being the answer. Okay, so we found the inverse following the result that I just quoted, that if you perform the Gauss-Jordan steps on the identity, you'll get the inverse. Now, finding the inverse of a matrix is kind of a lot of work. Gauss-Jordan is kind of a lot of work. Imagine if the matrix was 100 by 100, I wouldn't be keen. Why would you do such a thing? That is, the person can say, well, I already knew how to solve linear systems. Why are you so keen? So I'm going to illustrate one example of why you might want to do such a thing. There are lots of examples, and there's also the knowledge that you gained, but I'm going to illustrate one example of why you might want to do such a thing. So here's a linear system. Do you recognize that matrix of coefficients? It's the one from the prior slide. Here's a linear system, and I wrote 2, 12, 4. I just made up 3 numbers and put them over there for the constants. Gives this matrix equation, again using the matrix that we found the inverse of in the prior slide. We saw already that you can use the matrix inverse to solve this matrix equation. You multiply it from the left on both sides of the equation. When you multiply the matrix inverse from the left on this side of the equation, the matrix and the matrix inverse cancel, and you just get the vector of unknowns. When you multiply the matrix inverse onto the other side of the equation, the right-hand side of the equation, here it is, matrix inverse multiplied by the right side of the equation, and you get something that's, again, just a little bit ugly with thirds, but anyway, it's the answer, so that's what I want. X equals 16 thirds, etc. Okay, all right. So what was the point again? Here's the point. I wrote down a linear system that looks like the one from the prior slide, but it's just a little different. You see that that has a 2 and that has a 1? I'm able to, with the matrix inverse, I'm able to very quickly solve this one. Of course, I get a somewhat different answer because I started with a somewhat different question. This process where you have the same system on the left-hand side but slightly different right-hand sides comes up a lot in practice as an example of where matrix inverse would be handy. I'll name a specific example rather than just wave my hands around. So, for example, economists often use linear systems to model what happens in an economy. So the people who are buying steel cause the price of steel to go up, and because the price of steel went up, the price of automobiles is going to go, all this kind of stuff. So they often use linear systems to model what's going to happen in the economy, and they say, well, next year we're predicting. One of the things that a person should do when they make predictions is they should try to see how accurate the predictions are. In one sense that the predictions would be accurate is if you take your expectations for next year, I expect this to be 2 next year, and you change it slightly. What if instead it's 1? Then you're interested in how that changes your model's prediction. If your model's prediction changes drastically depending on what you write down for these numbers, why then you got to be very careful about what numbers you put here. So that's called sensitivity analysis. How sensitive is the result, 14 thirds minus 1 third minus 8 thirds, how sensitive is the result to changes in the assumptions? And what we see here is that once you have the matrix inverse, you can rapidly get answers for changed assumptions. So that's an example where you'd want the matrix inverse. It gives you some idea of how to proceed quickly. Okay, almost done. So with the 3x3 matrix, the one that I just did was a 3x3 matrix. With the 3x3 matrix, you can imagine going through and writing A, B, C, D, E, F, G, H, I, and doing Gauss's method. Right? You have an A, B, C, D, E, F. So you're going to say something like, well, minus D over A times row 1, add to row 2, and that'll use the A to eliminate the D. And you can do that. I've done it. It takes a long time. It's a bit of a pain. It's one of the answers to the exercises, but you can do it. It's not so much of a pain if you just do it with 2x2s, though. With the 2x2 matrix, it's not really very much trouble at all. You can ask yourself here, I'll put A, B, C, D, and on the other side of the matrix, I'll put 1, 0, 0, 1. And I'll take minus C over A, row 1, add to row 2. That'll use the A to eliminate the C, and you follow that through. You get all the letters, and again, in one of the homework exercises, you get all the answers are in terms of letters, and it's a little bit fiddly, but not too bad. When you do, you find that the formula for the general 2x2 matrix ABCD's inverse is this. It's a fraction. You might remember with the matrix A, it was a bunch of thirds. So the fractions come up here. We'll see why in the next chapter. But fractions come up here. So the fraction in this case has for the bottom of the fraction A times D. So you multiply the corners. A times D minus B times C. That's just how what it works out when you do the letters. That's just the way it works out. And then what are the entries? So the entries are, you see the A and the D, you interchange them, and you change the sign, the SIGN, of the off-diagonal entries. And so the inverse for a 2x2 matrix is calculated using this formula. It's worth memorizing this formula. 2x2, needing to solve 2x2 equations comes up reasonably often, and a person can, if the numbers are straightforward enough, a person can do this in their head. So it's worth memorizing this particular formula. Okay, and the computation is exercise 21, but it's a little bit fiddly, but not too bad. Maybe 1 page of paper. Here's an example, 2, 4, minus 1, 1. So let's see, where do I get the 1/6? 2 times 1, that's AD, minus b times c. B times c is minus 1 times 4, so that's 2 minus a minus 4, so that's the 6. And then what are the entries again? So you got to flip, DNA flip. So you got to flip the 2 and the 1, 1 and 2, and you got to change the sign, change the SIGN of the 4 and the 1. So the 4 becomes a minus 4, and the minus 1 becomes a plus 1. And when I carry through the 1/6, that's what I get. So it's worth memorizing this particular one. I don't know about memorizing the 3x3, but it's worth memorizing the formula for the inverse of a 2x2 matrix. It's not too bad at all. Okay, very good, very good. So let's see, for next time we're going to move to a new chapter, so we're going to be doing something different. We'll see what happens to, for example, the representation of a vector when you, with respect to a basis, when you change the basis. Okay, very good.